Hi there, students. If you are tuning in, and apparently you are, we are here to talk about the notes over atomic structure. I've probably given you a paper packet at this point and said, hey, go watch a video and fill this out. Well, I've still got a link to that video, and you are more than welcome to go tune into it. If you do end up watching the whole thing, I highly recommend putting on closed captions. That way you don't have to listen to the terrible, terrible music and fall asleep to it. But a request that I've had of students in the last few years has been to kind of make a short version of all of that. So you can still get the notes and you can still fill out what you need to fill out, but you don't have to sit through the awfulness that is the atomic structure video. So that's what this is going to be about. At any point during this video, I encourage you to pause things so that you can get down diagrams whenever those come up. And if there's something that you don't quite catch from what I'm going to talk about here, then again, I encourage you to go watch the original video to pick up any bits that I might miss. So without further ado, let's start with your notes over on page 1. First of all, this video and our notes here are going to cover 4 different experiments which were performed between the years of 1870 and 1940. And you're going to need to know a little bit about each of those experiments, sort of who did them, what we learned about the atom from each one, and some of the people involved. So the video kind of starts by talking a little bit about graphite. You know, the stuff you have in your pencil. We all know graphite. You've used it for years and years to make sketches. You probably have also noticed that if you do a big patch of graphite on your paper and then sort of rub your finger across that, it feels slippery. And so the question comes around, okay, well, why is graphite slippery? At an atomic level, graphite, which is modeled right here, is made up of pure carbon. Each of these black spheres here represents a carbon atom. And each one is bonded to 3 or 4 other carbons. And the reason why it's slippery, according to the theoretical model, the reason why it can get on your fingers, it's even used actually as a lubricant, a dry lubricant whenever you need to have parts slide past each other. If you take a little bit closer look at the atoms and kind of rotate them just right, you'll see that they're actually arranged in layers like this. And it's these layers that when you apply pressure to it, they're able to kind of slide past each other, which explains the slipperiness of graphite. Now that's theoretical. Using electron microscopes, we can actually look at a graphite crystal, and that's what you're looking at right here. You're looking at different rows of atoms, and as we zoom in even closer, and this video came out in the late 80s, early 90s, and so I'm sure imaging technology's gotten even better since then. We can actually discern these layers of atoms, and you can kind of see in your video there, they're sort of sliding past each other. The word atom, oh, I'm missing a picture. I wonder where it went. That's a shame. Now, if you take some of this graphite, say what we've got here on this guy's finger, or what we've got here in the pencil, and if we were to take a blade and cut it into 2 smaller pieces, and then take one of those and cut that into smaller pieces, and keep cutting, then in theory we would get to a point where we had a piece that was so small that even if we had a really sharp knife, we could not cut it. The Greeks were the first ones to come up with this idea. In fact, there was a Greek philosopher by the name of Democritus, And he came up with the idea of this particle that was so small you couldn't cut it, and he called it atoma, which is where we get the word atom from. Atoma literally means not cuttable. So that takes us through some of the background. Now, how did we figure all of this stuff out? Well, like I said, it started off with an experiment, and the first experiments we're going to talk about are using something called cathode rays. I'll go ahead and get the picture pulled up here. You can, of course, pause this at any point if you want to jot down what it's asking you to jot down and draw this. Pretty much, it is just a glass tube that's had most of the air pulled out of it to where it's very low pressure on the inside, and it has two electrodes hooked up at either end. One is a positive charged anode, and the other one has a negative charge. It's called the cathode. And so what's happening is that these particles were found to flow from the cathode end down to the anode end, okay, in the direction that you see here in the arrow. The person who found this out was a gentleman by the name of William Crookes, C-R-O-O-K-E-S, if you're writing this down, and you should be. He theorized that there were rays that were flowing from the negative cathode down to the positive anode in these glass tubes. Furthermore, he found out that if you took a magnet or a magnetic field, here we've got an electromagnet set up and it's turned off, but you can see here in this one, when they turn it on, that beam of cathode rays is bent. I'll turn it off again, turn it on again. And so the very fact that these could be deflected with a magnet suggested to Crookes that these rays, or these particles, had an electric charge of some kind. They seemed to be deflected toward the positive end. So, and also they were attracted to the positive end of the cathode ray tube, which is what gave them the idea that they were talking about something that was negative. They kept experimenting with these cathode rays, and one of the things they wanted to find out is, were these cathode rays pure energy or were they a particle of some kind? And so to test this out, what they did, and it's really clever, they built this little apparatus inside of the tube that had a little glass paddle wheel on it. And each of the little prongs on this paddle wheel had a little bit of phosphorescent coating, which when it was hit by these cathode rays, it would glow, so they knew that they could have it right in the path of this beam. And so whenever they turn this on, there's the wheel right there, and you can see what happens is that it caused the wheel to start spinning and actually push the wheel toward the other end of the tube. Now what that told them is that these cathode rays were actually particles. And furthermore, they were particles that had a certain mass, because you have to have mass in order to impart momentum to something else. You've got to smack into it and transfer that energy over. A really clever gentleman by the name of Joseph John Thompson, who we'll be talking about some more here in just a minute, went on to discover that these cathode rays actually exist in all known substances. He found them in all kinds of gases, for instance. Then he was able to, using experiments with different substances and cathode rays, he was able to measure the charge to mass ratio. They knew that these things were very small, but they didn't know how big. But they did know that the charge to mass ratio was 1.76 times 10 to the 8th coulomb grams. You don't really need to worry about that. What you do need to know is that they did have a certain definite charge. Now, the next experiment we'll talk about, a gentleman by the name of Milliken, Robert Milliken, built something to try and measure the exact charge and therefore find the exact mass of these cathode ray particles. And his apparatus looked something kind of like this. What you had is you had a box, basically. And inside of that box, you again had negative and positive electrodes. At this time, the electrodes were great big plates, big metal plates. And they had negative electricity coming to this one, positive current going to that one. And then there was a little bag that they could squeeze, and they could shoot little particles of oil in here. So some little particles of oil, some little oil drops would fall through the hole in that top plate and end up between these two electrically charged plates. Then they would hit those with a little X-ray machine, and what that would do is that would cause these little particles to be charged with cathode rays. Now, gravity was pulling these little droplets down, but they could also change the voltage of what was going through these plates, and so they could vary the electric force. And by getting it to a very certain point, they were able to keep these oil particles from falling, but they also kept them from going up toward that plate, and they balanced them to where they were just floating in midair. When they balanced them floating in midair, they then took the charge that they had of that electrical force, so they suspended those droplets, and that let them figure out both the charge and the mass of those electrons. They found out that the charge on an electron, which, by the way, that's what a cathode ray particle is, but now it's got a name. They called it electrons because it had that electrical charge, had a charge of 1.6 times 10 to the negative 19 coulombs, which is really, really tiny electric charge. But again, we're talking a really, really tiny particle, because these particles were about 9.1 times 10 to the negative 31st kilograms. Ridiculously, ridiculously tiny. And so that's how we discovered that electrons are a thing. Next experiment were done by a gentleman named Eugene Goldstein, and he, when he was playing around with cathode rays or cathode ray tubes, he found out that there were some other particles that would every once in a while smack into the other end of the tube. They weren't going toward the positive end, they were going toward the negative end. And they didn't seem to come from down at the positive end. They seemed to kind of materialize in the empty space in between that cathode and that anode. And he made a special cathode that had little holes in it that he called canals. And he was able to get some of these particles when the cathode rays were flying this direction. He found out that these other rays, these other particles, seemed to be flying that direction, and he named them canal rays because of these little canals that were in that cathode. You can go back to your first sketch that you made of this, and you can add canal rays in, and you can show the direction that they're flowing. They're flowing in the opposite direction, which showed that they had a positive charge instead of a negative charge. And so, finishing up your notes here on page 2, down toward the bottom, it was theorized that these canal rays happened whenever these electrons, which were coming from the cathode and going this direction, they would run into atoms of gas that were in that tube. And when they hit those atoms, they would knock one or more electrons loose. And so those extra electrons would continue toward the positive cathode end, or the positive anode end, I'm sorry. And these other particles that were left over now had a positive charge. Well, they were what were being drawn toward that opposite end. It formed positive ions. Okay? And so this is where these canal rays came from. Goldstein did the same kind of thing that Thompson had done. He started playing around with magnetic fields, and he found, like he expected, that these canal rays were drawn to the negative point, or the negative plate on a magnetic field like that. A New Zealand scientist named Ernst Rutherford found canal rays in hydrogen gas, and he found the smallest ones that could be found up to that point in hydrogen. And he ended up calling these protons. He showed that they were present in all kinds of matter. So at this point, by 1886, 1890-ish, we had gone from just atoms being a theoretical idea that the Greeks had of something that was not cuttable, to finding these negative particles, which we named eventually electrons, to finding these positive particles called protons. But at that point, we really didn't know how they were put together. So if you look at the third page of your handout, Joseph John Thompson proposed a model of the atom, which basically just said, hey, an atom is a thing that's got some positive protons thrown in there and some negative electrons thrown in there. And it was referred to as the plum pudding model, because a popular dessert at the time was this stuff called plum pudding. And if you kind of think of, if you've ever had Jell-O that has like chunks of fruit stuck in it, where you just got this blob of Jell-O and these random little grapes and pineapple chunks and stuff stuck in there willy-nilly, that's kind of what he theorized an atom would be like, but there wasn't really any definite distribution. In the box off to the right of your diagram there, that you're of course pausing this and making, this would also be like the blueberries in a blueberry muffin, or the chocolate chips in a chocolate chip cookie. They're just randomly embedded in that. Ernst Rutherford wanted to test Thompson's model. Thompson put forward this model, and at this point this is the best model of the atom that we had, but he wanted to test it, and that's where our next experiment's going to come in. It's called the gold foil experiment. And this one's really cool. This is the next diagram you need to make, by the way. What Rutherford did is he got a radioactive source that would spit out these particles called alpha particles, which are basically just the positively charged nuclei of hydrogen atoms. But they didn't know that at the time. They just called them alpha particles. They shot them in a straight line from a little cannon toward a very, very thin sheet of gold foil. And they used gold because you can get gold really, really, really thin. And so what he was doing is he was testing Thompson's model by setting up this sheet of gold foil, and he shot these particles at this sheet, and then when they got through, they would hit a screen on the opposite end. Now, the screen he made in the shape of a ring. It wrapped all the way around in 360 degrees, or almost 360 degrees. And anytime one of these particles would hit this screen, it would light up. It would make a little bright spot for just a second. And so what they were expecting to see happen, their hypothesis was, if the Thompson model was correct, then these particles that were going to fly through this sheet of these gold atoms and come out pretty much unscathed, pretty much unaffected by having all of those atoms right there. They would fly straight, and so what they would end up seeing is a whole lot of little spots directly across from that cannon. Interestingly enough, what actually happened is that some of those particles went straight, but there were also several that went off in different directions. And they scattered really, really widely, which is not what they were expecting to have happen. Some of them even seemed to hit that gold foil and bounce right back. So they were deflected or they bounced right back. Really funny quote from the video. Two of the guys that were running this experiment for Rutherford, Hans Geiger and Ernst Marsden. Geiger you are probably familiar with because the Geiger counter, which is an instrument that's used to detect radiation, radioactivity, was named after him. They did not expect this at all. They said that having one of these things hit this foil and then bounce back, they said it was if you fired a 15-inch shell, so like, a 15-inch long shell of artillery or something, at a piece of tissue paper, and it came back and hit you. So very, very surprising for them. They didn't expect this to happen at all, because remember, the hypothesis said that if you've got just random protons and electrons in there, there's not going to be anything big enough for these particles to hit and bounce off of. But in reality, their observation suggested that atoms had an area in the middle that had very high charge and very high mass. And it was these high charge and mass areas that were causing these particles to be deflected and bounce. And so they named this part of the atom the nucleus. And Rutherford came up with, the Rutherford model, or the nuclear model of the atom. And there's a place on your next page, page 4, for you to draw this. The nuclear model, and you can fill this out in the box to the right there, all of the protons are concentrated in a nucleus, a very small region in the center of the atom, with much smaller electrons occupying the rest of the atom's space. Okay, so they were very small, but they took up a lot of space. Just to give you an idea of how much empty space that an atom is made up of, if you imagine you took a golf ball and you put it in the middle of a stadium, middle of a soccer field or a football field or something like that, and that golf ball was the same size as the nucleus, how far out would you expect the electrons then to stretch? Well, it turns out that if you had that golf ball in the center of the field, the electrons would actually stretch out beyond the stadium out into the parking lot. So these very tiny electrons are taking up a tremendous amount of space in these atoms. And so it turns out most of an atom is empty space. This right here is kind of depicting what it's like. We've got a really tiny nucleus at the center, and then electrons arranged in the outside, sort of in a cloud. In 1932, a gentleman named James Chadwick found another part of the atom that didn't seem to have any charge, but it still had quite a bit of mass. He named it the neutron because it was neutral. It had zero charge, but it had about the same mass as a proton, as well as being found in the atom's nucleus. And so the mass of an atom is made up of the particles that are in the nucleus. So you take the mass of all the protons, you add them together with the mass of all the neutrons. The electrons have almost no mass, and so you don't even really worry about counting them. In the nucleus, you've got protons and neutrons kind of semi-haphazardly arranged in roughly spherical structure. And again, that's way down at the center of a much larger space, and most of that space is empty. The video at this point talks about something called nuclear notation. And again, you can pause to get this down, but then I suggest you start it back up so you can listen. If you've ever seen the symbols that are on the periodic table, this X right here would symbolize, say, an atom symbol, like you see on the periodic table. Carbon would be letter C, hydrogen would be letter H, nitrogen would be N, etc. It's going to have two numbers that go with it. There's a number here which is symbolized with the variable A. That's called the mass number. That's equal to the protons plus the neutrons that are in the nucleus of that atom. This number down here, which is symbolized by variable Z, is what's referred to as the atomic number. The atomic number is just the number of protons. Now, if an atom's neutral, meaning that it's got equal numbers of positive and negative charges, then that also is the number of electrons. Because remember, electrons have an opposite charge. They're negative, whereas the protons are positive. But those two charges are actually equal. Even though the electron's a lot smaller, it has an equal opposite charge. So the atomic number, big thing that it determines is the atom's type, or the element's type. For instance, every carbon atom has 6 protons. Every nitrogen atom has 7, every oxygen has 8, every hydrogen has 1, every helium has 2. And it's that atomic number that tells you what kind of atom, what kind of element you're dealing with. Now, not every atom is perfectly identical. There are different varieties of the same kind of atom. They're called isotopes. And so if you see here, here's 3 naturally occurring isotopes of carbon. About almost 99% of all the carbon on the planet is what we call carbon-12, meaning that it has a mass of 12. It's got 6 protons and 6 neutrons. But every once in a while, you do run into a couple different flavors of carbon. About 1% of all the carbon out there is what's called carbon-13. Now, it still has 6 protons, but it has 7 neutrons, and 6 plus 7 make up 13. So its mass is just a little bit more than this regular carbon-12 over here. And even rarer still, you've got what's called carbon-14. Very, very small percentage. That has 6 protons and 8 neutrons. And they're referred to as isotopes. They have different masses. Okay, everything else about them is the same. But because they have different number of neutrons, they do have different masses. We're up to the last page of the notes. Everybody say yay. We've got 2 more models to draw. On your last page here, this is what's referred to as the Niels Bohr model, or the orbit model. And Niels Bohr, who was a Danish chemist, I believe, he came up with the idea that these electrons actually moved in little fixed orbits, kind of like planets around the sun. There were a lot of problems with this model, one of which is that it didn't really make sense, because in order for something to circle something else, it has to radiate energy. And if it radiates too much energy, then eventually it's going to crash into whatever it's orbiting. And these electrons, as far as we know at this point, don't do that. So again, you've got protons in the nucleus, you've got electrons in these little orbital paths around the outside. About 20 years later, and we'll talk more about this when we talk about electrons and learn some of the rules for their behavior in the modern model of the atom, we got something like this. This is what's called the wave-particle model, or the quantum mechanical model. Now in this one, you've still got a nucleus at the center, but instead of definite orbiting paths, you've basically got little clouds, little regions of space where electrons tend to spend most of their time. They're not following a definite round orbit or anything like you always see in pictures. They can randomly be anywhere outside here, but they are more likely to be found where you can see that this is a little bit denser, or it's a little bit darker. Whereas these spaces in here in between, you might find an electron, but they're much more rare. And so both of these models, if you're wanting to get your last word on there, predict that electrons occupy specific levels of energy outside of the nucleus. And I'll leave you here with one last picture. Let me shrink my head here. So we go over here from original picture of the atom, which actually a guy we didn't mention named John Dalton, English chemist, came up with. He revived the old Greek atomic theory in 1808. After that, the first major development, remember, came from Joseph Thompson, who came up with a plum pudding model. Ernst Rutherford came up with the nuclear model. Niels Bohr came up with the orbiting electrons model. And then finally, in the 1930s, 1940s, folks like Heisenberg and Louis de Broglie and some other guys we'll talk about later came up with the wave-particle or quantum mechanical model. So that should take you through the easy version of the notes on atomic structure. So I wish you the best of luck. If you have any questions, feel free to catch me in class, and I'll be talking to you soon.